Hello, this is Richard Collins, your instructor in ATM101. Welcome to Water, Unit 5 of ATM101, Weather and Climate of Alaska. This unit explores the meteorology of water in the Earth atmosphere and highlights the unique properties of water. Water is required for life on Earth, and the United Nations recognizes that access to water is a major, if not the major, concern in planning for climate change. It's worth noting that 25% of the world's population currently lack access to safely managed water. In this unit, we investigate the following topics: how water is transported in the atmosphere, how water changes phase and the energy changes associated with those phase changes, how water in the atmosphere is characterized and measured, and how the meteorology of water is represented in weather maps. This lecture supplants our textbook Weather, a concise introduction by Gregory Hakim and Jerome Patou, with material from the textbook Meteorology Today by C. Donald Ahrens. Before we get into all the details, let's take a look at the big picture, the hydrological or water cycle. The hydrological cycle describes how water moves through the Earth's atmosphere and how it changes phase in doing so. Water enters the atmosphere from the ocean through evaporation, about 85%, and from the land through evaporation and transpiration, about 15%. The water in the atmosphere rises and condenses, forming clouds. Eventually, the liquid and solid cloud particles grow large enough and fall out as precipitation on the land or ocean. Precipitation includes rain, snow, hail, drizzle, sleet, etc. The weather that falls on the land has a complex journey back to the atmosphere. It can travel as groundwater via rivers and lakes and runoff back to the ocean, or it can travel directly through transpiration and evaporation from the land. At any one time, the total amount of water vapor in the atmosphere represents about a week's worth of rain. This should not be a source of panic because the hydrological cycle is exceedingly efficient in replenishing the water vapor in the atmosphere on a day-to-day basis. In the range of temperatures found on Earth, called the terrestrial temperatures, water can exist in all three phases of matter, as a solid, liquid, and/or a gas. As the water moves between these phases, it changes structure and hence its energy. As we discussed earlier, water molecules like to stick together due to the electric charges in the water molecule. Solid water, or ice, has water molecules locked in a crystal lattice with the lowest energy. Liquid water has molecules that move and have more energy. Finally, gaseous water has molecules that have the fastest motion and largest energy. To go from solid to liquid by melting and gas by evaporating requires energy that is absorbed by the water. The energy required to change the phase of a substance is called latent heat, as it is the heat that does not change the temperature of the substance. For example, ice at 0 degrees Celsius melts to water at 0 degrees Celsius. Conversely, latent heat is released when water condenses from gas to liquid and freezes from liquid to solid. These energy changes are an important factor in the formation of clouds and storms. While we are most familiar with melting, evaporating, condensing, and freezing, we also have the direct transition from gas to solid called deposition and from solid to gas called sublimation. Temperature is the measure of the average kinetic energy of all the particles in a solid, liquid, or gas. However, some of the particles have higher kinetic energy as some are moving faster than average, and some of the particles have lower kinetic energy as they are moving slower than average. For a liquid, some of the higher energy particles escape from the liquid and enter the vapor state. They evaporate. Some of the particles in the gas re-enter the liquid. Thus, there is a dynamic equilibrium where particles move back and forth between the liquid and the gas phase. Consider a covered beaker that is partially filled with water. Water molecules will escape the fluid and enter the gas phase. Eventually, a dynamic equilibrium is set up where there is a constant amount of water in the vapor phase and a constant amount of water in the liquid phase. For example, at 10 degrees Celsius, 50 degrees Fahrenheit, or 283 Kelvin, the vapor pressure of the water vapor is 12 hectopascals, or 1% of the air above the liquid. At 25 degrees Celsius, 77 degrees Fahrenheit, 298 Kelvin, the vapor pressure increases to 32 hectopascals, or represents 3% of the air. And at 40 degrees Celsius, 104 Fahrenheit, or 313 Kelvin, the vapor pressure increases to 74 hectopascal, or 7% of the air. Remember, this is a dynamic equilibrium. The molecules, in this case, for water, are moving back and forth between the gas and liquid phase. For every molecule that enters the liquid, another escapes to the gas, and so the average humidity is maintained. The air is now saturated, holding as much water vapor as possible, given its temperature. In the open beaker, the molecules escape from above the water into the gas phase and migrate away. The rest of the room is less humid, and so the water molecules do not meet other water molecules to collide with and condense. So all the water eventually escapes from the beaker, and the beaker dries out. Similarly, the ocean humidifies the air above it. If dry air moves over the ocean, more molecules will leave the water than join the water. Eventually, a dynamic equilibrium is set up with a constant vapor pressure over the water. In winter, dry air from Canada flows south over the Great Lakes. In passing over the lakes, it is humidified, and the humidity falls as snow over the land south of the lakes. This is called lake effect snow. The concentration of water vapor in air is called the humidity. Traditionally, chemists characterize the concentration of a substance in terms of the mass per unit volume. The mass per unit volume is called the absolute humidity. We can also express the concentration as mass of water to mass of air in a given volume. This is called the specific humidity. This makes more sense in meteorology, as often a parcel of air will change volume, for example, expanding as it rises and contracting as it falls. So if the amount of water in the parcel of air does not change as it rises and falls, the specific humidity sensibly stays constant, while the absolute humidity will vary. The mixing ratio is the ratio of the mass of water to the mass of dry air in a given volume. We can also express the amount of water vapor in terms of the pressure it exerts. All gases exert pressure. We will discuss this in more detail later in the semester. Finally, we consider the amount of humidity in terms of the amount of water present to the maximum amount of water the air can hold at that temperature. The ratio of the actual vapor pressure of the water in the air to the maximum possible vapor pressure, or capacity of the air to hold water, is called the relative humidity. The maximum possible vapor pressure is called the saturation vapor pressure. Air at 10 degrees Celsius has a saturation vapor pressure of 12 hectopascal, while at 40 degrees Celsius it has a saturation vapor pressure of 74 hectopascal. So at 10 degrees Celsius, a parcel of air with vapor pressure of 10 hectopascal has a relative humidity of 10 over 12, or 0.83, or 83%. At 40 degrees Celsius, that parcel with the same amount of water has a relative humidity of 10 over 74, or 0.14, or 14%. Why is this useful? Well, the relative humidity is telling us how likely condensation is going to occur. This is critical in understanding cloud formation and precipitation. At a relative humidity of 100%, the air is saturated and condensation or cloud formation can occur. At a relative humidity of 83%, condensation is likely, while at 14%, condensation is unlikely. The analogy I use is that the capacity of air to hold water is like a bucket. The size of the bucket increases with temperature. As the air becomes more humid, the bucket fills and eventually overflows. The overflow is condensation. The percentage of the bucket that is full is the relative humidity. At low temperatures, a given humidity may fill the bucket and we have a relative humidity of 100%. At higher temperatures, with a bigger bucket, the same humidity only fills part of the bucket and the relative humidity is lower. Saturation vapor changes with temperature as air can hold more water molecules in vapor as the temperature increases. This is because at higher temperatures, the water molecules are moving at faster speeds and less likely to stick together when they collide and ricochet. Thus, the capacity of air to hold water increases as air warms. At 10 degrees Celsius or 50 degrees Fahrenheit, the saturation vapor pressure, ES, is 12 hectopascals. At 30 degrees Celsius, 86 degrees Fahrenheit, ES increases to 42 hectopascals, and at minus 20 degrees Celsius, or minus 4 Fahrenheit, ES decreases to 2 hectopascals. Let's assume the humidity has a partial pressure of 2 hectopascals. The relative humidity changes with temperature. At minus 20 degrees Celsius, the relative humidity is 2 over 2, equal to 1. are 100%. At 10 degrees Celsius, the relative humidity is equal to 2 over 12, equals 0.17, or 17%. And at 30 degrees Celsius, the relative humidity is 2 over 42, equal to 0.048, which is equal to 4.8%. Consider a given relative humidity at 100% at minus 20 degrees and 10% at 30 degrees Celsius. 100% humidity at minus 20 degrees Celsius has E equal to 2 hectopascals. 10% humidity at 30 degrees Celsius has an E of 0.1 by 42 hectopascals, or 4.2 hectopascals. Thus, the air with 10% relative humidity is more humid than the air with 100% relative humidity. And we'll often find that in desert regions where it is very hot and very low relative humidity, the air is actually more humid than the air in cold, dry regions. The plot also shows the difference at low values of vapor pressure over ice and water, and this is an important factor we'll see later in cloud formation. Consider what happens as a parcel of humid air cools. A parcel of humid air at 20 degrees Celsius, or 68 degrees Fahrenheit, or 293 Kelvin, with a vapor pressure of 15 hectopascal, has a saturation vapor pressure of 23 hectopascal and a relative humidity of 65%. The horizontal axis of the plot is reversed and we move to the right as the temperature decreases. As the air cools, the saturation vapor pressure decreases. The vapor pressure remains constant and the relative humidity rises. At 13 degrees Celsius, the saturation vapor pressure reaches 15 hectopascal and the relative humidity reaches 100%. The air is now saturated and condensation can now occur. As the temperature falls further, the saturation vapor pressure decreases further and the air loses the excess water, while the relative humidity stays at 100%. If the temperature where condensation occurs is above 0 degrees Celsius, then dew will form as droplets, while if the temperature is below 0 degrees Celsius, the condensation will form as frost. The dew point temperature is the temperature where dew or frost forms. This is the temperature where the air is saturated, the relative humidity is 100%, and condensation occurs. In our last example, the dew point temperature is 13 degrees Celsius. If the parts of air had started with a higher partial pressure of water vapor, for example 22 hectopascal, the dew point temperature would be 19 degrees Celsius, as the saturation vapor pressure of water is 22 hectopascal at 19 degrees Celsius. If the parcel of air started with a lower vapor pressure of water of 12 hectopascal, the dew point would fall to 10 degrees Celsius. So we see that the dew point temperature decreases as the humidity decreases. Another way to think of this is that as the humidity gets lower, we have to get to lower temperatures to squeeze or freeze the water out of the air. The difference between the temperature and the dew point temperature is the dew point depression. If the dew point depression is small, the air is moist. If the dew point depression is large, the air is dry. There are several ways to measure humidity. A sling psychrometer uses two thermometers, a dry bulb thermometer, which is a regular liquid thermometer, and a wet bulb thermometer, which is a liquid thermometer with a wet piece of cloth over the bulb. The dry bulb thermometer measures the regular temperature T. The wet bulb measures a lower temperature TW, as it loses energy to the water in the cloth as the water evaporates. In dry air, more water evaporates and TW is much lower than T. In humid air, less water evaporates and TW is closer to T. So the difference, the wet bulb depression, T minus TW, and the air temperature T are used to determine the dew point temperature and hence the relative humidity from tables. The absorption properties of water can be used to measure humidity by a beam of infrared light passing through an air sample. As the humidity increases, more light is absorbed and the beam is dimmer. The dimming of the infrared light is measured and used to determine the humidity. Alternatively, a satellite can detect the infrared radiation emitted from water in the atmosphere. The IR signal increases as the humidity increases. Electric hygrometers are based on the fact that humidity can change the properties of electrical components. Changes to resistance and capacitance can be detected and converted into a measurement of humidity. Finally, the chilled mirror hygrometer shown in the figure is used in current automated surface observing systems ASOS and automated weather observing systems AWOS. A mirror is connected to a cooler so that the temperature of the mirror can be controlled. A beam of light is reflected off the mirror and detected by a photoelectric sensor. When the temperature of the mirror is above the dew or frost point, then the mirror remains clear and a strong signal is detected by the sensor. Once the mirror cools to the dew or frost point, water condenses or ice forms on the mirror. Now the reflectivity of the mirror is reduced and the signal detected by the sensor decreases. The temperature where the signal decreases is recorded as the dew or frost point. For measurements to be accurate, the mirror must cool and warm uniformly with a metal block and a heat sink. The thermometer must be well connected to the mirror through a metal block. The air must be well mixed to condense or frost evenly so that there must be a uniform airflow across the mirror. Humidity is represented on surface weather maps using our station model where we report dew point temperature. The map to the left shows the southeastern United States on the 20th of February 2014 at 1800 UTC or 1200 CST. In the map shown, we see lower temperatures to the northwest in the blue circle. For example, we see a temperature printed in red of 7 degrees Celsius or 45 degrees Fahrenheit and a dew point temperature printed blue of -1 degree Celsius or 30 degrees Fahrenheit. The associated relative humidity is 56% and the water vapor partial pressure is 6 hectopascals. To the southeast, we see higher temperatures in the red circle. For example, we see a temperature of 24 degrees Celsius or 75 degrees Fahrenheit and a dew point temperature of 13 degrees Celsius or 55 degrees Fahrenheit. The associated relative humidity is 51% and the water vapor partial pressure is 15 hectopascal. We have crossed a cold front, where colder, drier air is behind the front and warmer, moister air is ahead of the front. The front is moving from west to east. The maps of dew point temperature and the temperature highlight how the changes in humidity and temperature are most pronounced around the cold and warm front. Clearly, we have a cold air mass to the west that is running into a warmer, humid air mass to the east. This is a classic situation in the wintertime, eastern lower 48. Cold, dry air masses from Canada travel south to meet warm, humid air masses traveling up from the Gulf of Mexico. The wind barbs show winds that support this picture. The winds are northwesterly behind the cold front and southerly ahead of it. Along the front, the winds turn to flow along the front. The temperature map also shows the location of Amarillo, Texas with an A, Dallas, Texas with a D, and Shreveport, Louisiana with an S. We will now look at meteograms and radio soundings from these cities. The meteograms from Amarillo show the temperature, dew point temperature, and relative humidity over a 2-day period. The passage of the cold front early in the morning of the 20th of February is indicated by the blue arrows. On the 19th of February, we see a diurnal cycle in temperature, while the humidity indicated by the dew point stays relatively constant. The relative humidity varies due to the change in temperature. The relative humidity is highest in the early morning when it is coldest, and the saturation vapor pressure is lowest. On the 20th of February, the temperature does not fall during the night. This is due to the presence of clouds and humidity associated with the front. The dew point rises with the passage of the front. We also see that the winds change direction abruptly from southwesterly to northwesterly as the front passes over Amarillo. As the front passes, the temperature falls about 10 degrees Celsius, the dew point temperature rises 8 degrees Celsius, and the relative humidity increases from 20% to about 75%. The concentration of water vapor has increased by a factor of 2. The increase in relative humidity reflects both the drop in temperature as well as the rise in humidity. The satellite images and radar maps in Chapter 2 also show the increase in humidity and precipitation along the cold front. After the passage of the front, it is cold and dry through the remainder of the 20th of February. On the 20th of February, Shreveport lies ahead of the cold front under the warmer and moister air mass, while on the 21st of February, Dallas lies behind the cold front under the colder, drier air mass. Winds aloft, above 600 hectopascal or 4 kilometers, are westerly at both sites. Surface winds are northwesterly at Dallas and southeasterly at Shreveport, consistent with their positions behind and ahead of the cold front respectively. The air is much more humid over Shreveport than over Dallas. Over Shreveport, TD is close to T, whereas over Dallas, TD is much less than T. The Dallas sounding reflects the presence of cold, dry air from the northern Midwest in Canada, while the Shreveport sounding reflects the presence of warm, moist air from the Gulf of Mexico. To investigate how the saturation vapor pressure of water varies with temperature, we considered the humidity of an air parcel of temperature 20 degrees Celsius or 68 degrees Fahrenheit and a dew point temperature of 13 degrees Celsius or 55 degrees Fahrenheit. The actual vapor pressure is 15 hectopascal, which corresponds to the saturation vapor pressure at the dew point temperature. Thus, the dew point temperature is a direct measure of the humidity. The relative humidity is the ratio of the actual vapor pressure at 20 degrees Celsius of 15 hectopascal to the saturation vapor pressure at 20 degrees Celsius of 23 hectopascal. 15 over 23 equals 0.65 or 65%. We can saturate air in three ways. First, we can increase the humidity by adding water vapor. This is what happens when we create evaporation fog. This process occurs over lakes and ponds in early morning, where the air cools during the night, but the water remains warmer. Humid air rises into the cold air. This is common in late July and early August in interior Alaska, where we see fog over ponds and lakes in the early morning. 2. We can reduce the temperature by cooling air and create radiation fog. This occurs at night when the ground radiates its heat and cools, thus cooling the air above it by conduction. The colder air now has a lower capacity to hold water, and the relative humidity rises, eventually forming fog. An extreme version of this is the ice fog that forms in Fairbanks during our extreme cold, dark winters. Finally, the third process is the cooling of air parcels as they rise in the atmosphere. We will see later why an air parcel cools as it rises, but it does. As it cools, the saturation vapor pressure decreases, the relative humidity increases, and eventually condensation occurs and clouds form. This process is visible in June and July in Fairbanks, where the afternoon sun heats the ground and creates thermals of rising air. Cumulus clouds form in this rising air as air condenses. Meteograms from Seattle, Washington and Bismarck, North Dakota highlight how humidity varies at a site under different meteorological conditions. Seattle is classified as a climate of CSB, C, moist with mild winters, S, dry summers, and B, long cool summers. Bismarck is classified with a climate of DFA, D, moist with cold winters, F, wet all season, and A, summers long and cool. So in February, we expect Bismarck to be colder, drier, and clearer than Seattle. Under clear skies, the diurnal temperature cycle is greatest with high daytime temperature and low nighttime temperature. So if the humidity is constant, the relative humidity will rise during the night as it cools, peak in the early morning, and fall during the day. Dew and frost is likely even though the days are warm. Under cloudy skies, the diurnal temperature cycle is smaller as nights cool less and days warm less. Again, if the humidity is constant, the relative humidity rises less during the day, peaks less in the early morning, and falls less at night. Dew and frost is less likely. With these ideas in mind, can you answer the questions on the slide? Finally, our summary and takeaways from Unit 5. Water exists in a hydrological cycle that moves water through the atmosphere and Earth very efficiently. Water exists in all three phases, solid, liquid, and gas. Humidity is defined in a variety of ways, some of which make better meteorological sense than others. Parcels of air change volume as they are carried by the winds. Specific humidity is a good measure, better than absolute humidity. Relative humidity gives the likelihood of condensation and therefore is very useful for understanding how water moves between vapor and clouds. Dew point temperature is readily measured and gives an absolute measurement of humidity. Saturation vapor pressure is the capacity of air to hold water at a given temperature. Relative humidity is the percentage of saturation of the current level of humidity. At saturation, relative humidity is 100%, the temperature equals the dew point temperature, and condensation occurs, and cloud, dew, and frost form. The difference between temperature and dew point is a measure of relative humidity, and dew point is used to identify changes in air mass and the passage of fronts.